Welcome to our discussion on modeling with equations. Here are the objectives we're going to cover. You can see that basically we're just going to discuss the technique very quickly, and then we're going to get into a bunch of examples. So feel free to skip around, watch the ones you think you want to watch, or just go try some homework. Also, to make things easier, I'm going to split all of these up and put each one of these questions. So each one of those examples, there's actually 8 of them, but each of the topics are going to be their own separate video. So you can either sit through this very long, about 38 or so minute long video to get all of the examples all at once, or you can just watch a couple of them and stop, and if you want to, come back later and just watch the individual videos for each of these particular topics. All right, so making and using models is basically a fancy way of saying, let's put together a set of simple steps that will help us solve word problems, right? We're trying to avoid the word problem because it has a negative connotation, but basically that's all we're doing is how do we get through all these messy word problems that we've been hating since our very early grade school days? Well, here's a nice set of 4 simple steps that we can apply to basically any word problem that we're trying to solve. And I'm going to add a couple of my own little things to here because this is a good starting place, and you guys should definitely add and subtract whatever you think works best for you. But I always tell my students that the first thing you should do before doing anything, and I'll put that down as step 0, right, is read the question, right? Read the whole thing. And you don't even need to do anything. Just read it, get an idea of what it's about. Is it a question involving distance, rate, and time? Is it a question involving mixtures? Is it a question involving geometric shapes and areas and distances, things like that? So is it a question involving money? Just get an overall idea of what the question is about. All right, and now you're going to go back after you've read it all the way through. Now you're going to read it in little bite-sized pieces, and you're going to pull out all the information you need. And the first thing you're going to look for is the variable. You're going to identify the variable. And what that means is you're really basically just identifying what the question is. All right, so when it says identify the quantity that the problem asks you to find, you're basically identifying the question. What do they want you to figure out? What is the area of the field? Okay, so my variable is the area of the field. How much of this liquid needs to be added to the mixture? Okay, so I'm looking for the quantity of this liquid, right? How much does it cost to rent the car? Okay, I'm looking for the cost of renting the car. So those are the, it's pretty obvious. It's usually the very end of the word problem is when the question is stated, but identify that, and then you're going to basically give that unknown a letter, because that's the thing you're trying to solve for. You don't know what it is, so that's your variable. So that's what you're identifying. You're identifying your variable. Now, common wisdom is to always give it an X, right? They even have it written right here. Call it X. But you'll also say, they say, or some other letter. Again, I tell my students, why don't we get in the habit of labeling it with something that makes sense? So if we're looking for the cost of renting the car, label it C for cost. If we're looking for how much of, the liquid that we need to add, call it L. Or if we're trying to solve for the width of the park, call it W. Things like that. So give it letters that make sense to you. Okay, now step 2. This is the biggie, right? Translate from words to algebra, which means, again, as you're going through these bite-sized pieces of the word problem, you're writing down everything it tells you, and you're trying, if you can, to write it in terms of math. Sometimes it's just a matter of copying down the bits and pieces of the question, because if you can put all this stuff kind of in your notes in like one little space, you don't have to keep going back and looking at the question. You just have everything right there on the piece of paper in front of you. And then here's the biggie. This is the granddaddy of them all. Always, always, always draw a picture if you can. Right? Sometimes you can't draw a picture. Some questions just don't lend themselves to pictures. But even something as simple as, drawing a rectangle to represent the park that you're trying to find the area of, or drawing some arrows, to represent a car is going in this direction and a car is going in this direction, and then we're going to try and find the distance between them. Something as simple as that's now going to tell you, hey, look at that. I've got a right triangle, and now I know I can start using some trigonometry and things like that. It'll give you clues as to the techniques you're going to use to solve that problem once you draw a picture. Okay, step 3 sounds a little vague. Set up the model. Well, basically, what you're really doing in step 3 is you're finding the hidden equation, right? Because all of these questions are asking you to solve for something, right? They want to know what x is. So that means x has to equal something. So that means there has to be an equation somewhere in that question that sets x equal to something. So there's got to be some sort of phrasing in there. The cost of the car is twice as much as blah, 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 blah. Well, then we know the cost of the car, right? We know C, because we're going to call that cost, is twice as much, 2 times whatever the blah, blah, blah was, right? The amount of the liquid is blank, and then so your L equals, right? The length is blank. And then sometimes it's not even that obvious where they'll just talk about the area of the park and these types of things. Well, you know that area is length times width. So there you have area is, right, length times width. And we've just set up the model, right? We've set up an equation. So setting up the model is a fancy way of saying set up an equation or equations, right? As we get more and more complicated, we'll have more than one equation. But the bottom line is if you only have one variable you're trying to solve for, right, one x or one L or one C, you only need one equation, right? You only need a number of equations to match the number of variables. So you can sometimes start with more than one equation, but sooner or later you'll be able to like substitute some things in and solve it down and pare it down and only have one equation. All right, once you've done that translation, and that really is probably the hardest step right there is coming up with the equation. Once you've done that, all you got to do is solve it and check it. I know that sounds like, oh, well, that's easy. Well, it is, right? Solving and checking, it's just going to involve some math. You move some stuff around, you use whatever techniques you have to use to solve for the type of problem that you have, and when you're done at the end, you always want to check your answer. All right, so with all that being said, let's look at some examples and see if we can apply these steps. Now, if you're good with this is the point where you can just stop this video and go off and try some homework. Okay, so our first one is a car rental company charges $30 a day and 15 cents a mile for renting a car. Helen rents a car for 2 days and her bill comes to $108. How many miles did she drive? So you see, I read it all the way through without doing anything. Now I'm going to go back and take it in little bite-sized pieces and write down everything they have. The first thing I'm going to do is I'm going to identify my question. How many miles did she drive? There's my question, right? So, as you can see, we're going to let x equal the number of miles driven. Now, if it was up to me, I would have called it m for miles, but you know, our author, our textbook loves to call everything x, but you know what's going on. All right, so step 1, we've identified the variable. Step 2, we need to translate these things. So we're going to start writing down everything they tell us in math. All right, so we know the number of miles driven was x. We know the cost, right, was 15 cents per mile. So that's 15 cents times how many miles. So there's 0.15 times x. So obviously we're going to do it in dollars because we need everything to be in the same quantity because we also have this daily cost of $30 per day. Now, why do we have 30 times 2 already? Well, if you go up here, she rented her car for 2 days, right? So we know that she paid $30 times 2 or $60 just to have the car for the 2 days, and then she had to add in the cost of the mileage. So just by thinking about that, and even if you just wrote down those words like we did here, right, that we wrote down mileage plus daily cost equals total cost, and that helps us go, okay, well now the algebra, this is what represents the cost of the miles, this represents the cost of the days, and then here's my total cost, because they told me it cost $108. And lo and behold, we have now discovered the hidden equation, right? We have the model, we have the equation, and we can solve it. So now we're on to the last step. So now we need to solve for x. So we subtract that 60 from both sides, right? The 30 times 20, and we're left with 0.15x equals 48. We, of course, divide both sides by 0.15. We do the math. X equals 320, and 320 miles is how much she drove. That should be our answer. One final step is to check it. Throw the 320 back into our equation and see that it does, in fact, give us the 108 that it's supposed to, so we know we have the right answer. All right, how about something involving interest? When you borrow money from a bank or when a bank borrows your money by keeping it for in the same as account, the borrower in each case must pay for the privilege of using the money. The fee that is paid is called interest, duh, right? The amount that's being deposited is the principal, and then of course the annual percentage rate is normally called just the interest rate. Now there's a very simple formula for very simple interest, and that's interest equals principal times rate times time. That's simple interest, guys. Keep that in mind. Nothing in the real world deals with simple interest, does not exist. This formula is a bunch of crap, but we use it in math as a learning tool. Just know that in the real world, nothing ever uses simple interest. It's always compound interest, which is a totally different formula, much more complicated, but this is, like I said, a learning tool. Okay, so remember, whenever, and this goes for any formula that deals with interest rates. Anytime you see an R anywhere in a formula in finance that represents rate, a 5% rate or a 3% rate, R is always written as a decimal. So 5% always becomes 0.05, 3% would become 0.03, 2.5% would be 0.025, and so on and so forth. So with this case, if we had a $1,000 deposit for 3 years at 5% interest, we would slam it into this formula and we get $150 because that's simple interest, right? We're basically just getting 5% of that $1,000 each year. So now, what if you've got 100,000 and you invested in 2 different accounts? This is a very common type of question, right? One of them gives you 6%, the other one pays 4.5%. You'd always ask yourself, well, why wouldn't you put it all in 6%? Well, maybe the 6% one is risky and you don't want to risk losing your money. Okay, so if her total interest is $5,025 per year, how much is invested at each rate? So we've read it all the way through. We've identified that it's a question that involves interest and money. So we're thinking, I can use that formula, interest equals principal times rate times time. And then we're going to go back and we're now going to do our second step, which is to identify the question. Well, how much money is invested? So X is going to be the amount invested, but it says at each rate, and we've got 2 different rates. So we're going to arbitrarily just pick the first rate. You could pick the second if you wanted to, and say X is going to be the amount invested at 6%. Simple, easy. Now, some of you might be thinking, okay, then Y is going to be right the amount at 4.5%, and that's fine. And then what do we know about those 2 amounts? We know that X plus Y has to equal all of the money, right? And then we also know something about the interest. We know that the total interest is 5,025. Well, how do we get interest? Remember, it's interest equals principal times rate times time. Well, here's our principal. Here's how much we invested. Here's our rate as a decimal. And our time, remember, is, what is it? What is it? What is it? Right? How much time? Well, 1 year, because it just said 5,025 per year. So time is just going to be 1 in this case. All right. So we can figure out how much interest we get from these 2 things, because total interest is going to be X times 6%. That's how much interest she makes off this account. And then we have to add how much she makes off the second account, which is Y times 0.045. And that whole amount, right, has to equal 5,025. So we now have 2 equations, right? We have this one and this one. And we have 2 unknowns. So we can solve 2 equations with 2 unknowns. What do you want to do? Right? There's a couple different ways. You can do the substitution method, the elimination method, the addition method. There's all sorts of different ways. So you see what I mean by you set things up and then you figure out how to solve it, depending on the type of situation you have. Now, another way to look at it is instead of using a second variable, you can think of the amount invested in the second account as being 100,000 minus X. But isn't that just taking this first equation here and solving for Y? Y would equal 100,000 minus X. There you go. Now you have both equations written in terms of X. And by substitution, you can now take this stuff and put it in for this Y here. And so you'll see what happens on the next couple slides. That's exactly what they did, right? You've got 0.06x and the 0.045 times that big whole junky stuff, which was what we used to have as a y. We put it all together because we know the amount of interest from the two things has to add to the total interest. We do a little math, we solve some stuff, we move stuff around, and we finally get 35,000 in for x. Of course, we can now take 35,000, subtract it from our total of 100,000, get the other piece, which is 65,000, plug both of those back into our equation and make sure that we actually get the 5,025, which we do. All right, how about area and length? So anytime you come across area and length problems, remember, you get this from reading all the way through and getting the overall flavor of the question. You're going, this is talking about area, so I should probably draw a picture and think about length times width, and if it's triangles, remember Pythagorean theorem and basic geometry and trigonometry, right? So it just gives you an idea of where to begin when you have to start solving these things. So here's a typical type of question. And I mean typical. You will see these types of questions time and time again. So once you learn how to solve one of them, the steps are the same. All you got to do is change the numbers and slightly change your picture maybe. All right, square garden, walkway 3 feet wide around the outer edge, as shown in the picture below. If the area of the entire garden, including the walkway, right, that's important. You gotta read the words, including the walkway, that's important, is 18,000 square feet. What are the dimensions of the planted area? All right, so we've identified our question. What are the dimensions of the planted area? So we're basically looking for length and width, right? What are these two dimensions? Of the planted area, right? Of the dirt, not including the walkway. All right, well, we've read all the way through. We've identified our area, right? We're looking for the dimensions. Remember that because this is a square garden, these two things are the same, right? Length and width are the same. So that's why we can just go ahead and call it x. Now, they tell us that there's a 3-foot walkway, so we can label this as 3 as we go through here, blah, 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 blah. The area including the walkway is 18,000. So doesn't that mean that if I take this whole length here and square it, it's going to be 18,000, right? Because remember, it's a square. So this distance up here is x, and then you've got 3 feet here and 3 feet here. So isn't that total length going to be x plus 6? And isn't this going to be exactly the same, right? Here's x, there's a 3 up there and a 3 up there, so it's also going to be x plus 6. So we're going to square that, and that has to equal 18,000. So you can FOIL this out, or if you remember your formulas, you know this is x squared plus 12x plus 36 equals 18,000. And now you have to solve that. Well, you recognize that as a quadratic, and you go, you know what? I can solve a quadratic very easily with the quadratic formula or by factoring, right? There are other ways you can solve it. You can solve it by grouping and things like that. And we're going to show you some other ways on the other slides. But the easiest way is to solve it as a quadratic. So if you know how to solve a quadratic, you're good to go, right? You have to bring the 18,000 over because you always have to set a quadratic equal to 0. So you get x squared plus 12x minus 17,963 equals 0. And now you can try to factor it, x, and you're basically looking for factors of 17,963 that have a difference of 12, right? Or sorry, add to 12 because they have to have a difference of 12, right? Because this is a negative number. So one of these is going to be negative, one of these is going to be positive. Obviously, the bigger number is positive because you have a plus 12 here. All right, let's see how else we can try and tackle this one. So far so good, just like what I did, x plus 6, right? Set it equal. Well, instead of setting it up as a quadratic, we could just take the square root of both sides. And this might make our math a lot easier. So whip out your calculators if you got them, and take the square root of 18,000. See, well, you don't get a whole number, that's for sure, right? That's not a perfect square. But you can work it that way if you want. And so x is going to equal, it's 134.164 minus 6. So it's basically, when you round, about 128. You can get a more precise answer if you want, but for what we're going to be doing, that's going to be good enough. Okay. Another example, more kind of geometry ones. A rectangular building lot is 8 feet longer than it is wide. It has an area of 29,000. Find the dimensions of the lot. Again, we identify the question, find the dimensions, so we need to know width and length, and then we go back and read it and pull out all the information it tells us. The lot is 8 feet longer than it is wide. So if W is the width, then isn't the length going to be W plus 8, right? It's 8 feet longer than it is wide. Now, if you had a hard time with this, and some of you might have thought, well, okay, so then doesn't that mean W equals L plus 8? If you plug numbers in here, you'll see that it doesn't work. So let this be a 4. Then this ends up being 12. And you ask yourself, is it 8 feet longer than it's wide? Is the length longer than the width? And you go, no, that doesn't work. So it's got to be this one, right? Translating can be a tough skill, but if you write this, right, the length, right, is 8 feet longer than the width. See how that works? Okay, has an area of 29,000. Well, what do we know area? Area is length times width. So 2,900 has to equal length times width. But we don't want an equation with two variables, so let's substitute. Equals W plus 8 times W, right? Because by substitution here. So 2,900 equals W squared plus 8W. And again, you're seeing the squared and the linear term, so you're thinking, uh-oh, quadratic, set equal to 0. W squared plus 8W minus 2,900. Solve your quadratic. All right, so here's my picture. Here's my length and my width. Translating things. Set it up this way. Subtract it, set it equal to 0, just like we said. And then, depending on how good you are at factoring, you can hopefully factor it. If you can't, you can use a quadratic formula. You come up with your two solutions of either 50 or negative 58. It's pretty obvious it has to be 50 because you can't have a width of a negative number, right? That doesn't make sense. So sometimes you'll get what we call an algebraic answer, that it works in the algebra of the question, but it's not a practical answer. It doesn't work in the context of the question, right? You can't have a width of a negative number. So you kind of toss that out as an impractical answer and you go, all right, width has to be 50, which means length is 8 more, so length has to be positive 58. And it's just a coincidence that that was a positive 58 and the other one was a negative 58, okay? All right, mixtures. This is a very common question. You see this a lot in chemistry classes. And there are all sorts of different types of mixtures. You can have actual chemical mixtures, but then you can have things like mix different trail mixes, and so that you have this many 25% peanuts, or they'll give you all sorts of different contexts. Okay, so let's look at an example. 10 grams of sugar is dissolved in 5 liters of water. Then the sugar concentration is obviously 10 divided by 5, or 2 grams per liter. Solving a mixture problem usually requires us to analyze the amount of some substance in a solution. So now here's a typical example. We've got a manufacturer of soft drinks advertises their orange soda is naturally flavored, although it contains only 5% orange juice. Some new law comes out and says the drink must contain at least 10% fruit juice. So how much pure orange juice must the manufacturer add to 900 gallons of orange soda to conform to the new regulation? So we read it through. Oh, it's a mixture problem. Okay, what parts of the mixture problem are we dealing with? Okay, well, it's got 5% in the beginning. It needs to be 10%. And we have 900 gallons, right? So we're picking out all the important pieces. We identify the question. How much pure orange juice must be added to 900 gallons of their soda? So X is going to be the amount of pure orange juice added. Okay, now we can draw a picture we want to and try and visualize what we're doing, but this would be kind of silly to waste our time doing this. But this is just so you can visualize it. All right, we got 900 gallons of juice that's got 5% orange juice in it. Then we're going to add a certain amount of pure orange juice to it. Don't know what that is, but when we're done, it's going to be 10% juice, and the total amount of liquid is going to be 900 gallons plus the X amount of gallons that we just added to it. Hopefully that all makes sense. So we can think of kind of the volume in two ways. The volume of the total mixture. So the total mixture is just going to be 900 plus X gallons. But we can also think of the volume or the amount of a certain thing in the mixture. And this is always the key to mixture problems, is getting that secondary equation always comes from looking at some quantity in your mixture, right? So in this case, we're looking at how much of our mixture is pure fruit juice, pure orange juice, right? There'd be another question where if it had to be 25% peanuts, then you'd ask, okay, how much of your mixture is peanuts? And so on and so forth. So in the original mixture, if it was 5% juice, then out of those 900 gallons, we take 5% of that, there were 45 gallons of pure orange juice. Now, when we add pure orange juice to it, that means we're adding all X gallons of pure orange juice, right? 100% of X is just X. So in the end, we will have 45 plus X many gallons of orange juice in our mixture. But more importantly, our finished mixture needs to be 10% orange juice, right? So if we take 10% of the 900 plus X, that gives us another equation that we know we have 0.1 times this has to be the same thing as 45 plus X. And that's where the hidden equation comes from, right? So we have all this stuff, right? X is how much is added. 900 plus X is the amount of the total mixture at the end. 0.05 times 900 equals 45. That's how much juice we had, right? X is how much pure juice we added. In the end, we need 10% total juice, right? So we need 10% of the total mixture, which is going to be 90 plus 10% of X. If we actually do this math here, right? 10% of 900 is 90, 90 plus 10% X. So now we know that the amount of pure orange juice, which was 45 gallons that we started with, the X gallons that we added, has to be the same thing as the 90 gallons that we'll have at the end, plus 10% of X. Now all we got to do is solve for X, right? So move this X over here to get 0.9X. Move that 45 over there to get 45. Divide both of them by 0.9, and you get 50. So they have to add 50 gallons of pure orange juice to bring it up to the 10%. And we can double check that and see that our amounts are equal. How about problems about time needed to do a job? So work-related questions. When solving a problem that involves determining how long it takes several people to complete a job, we have to use the fact that if a person or machine takes so many time units to complete a task, then in 1 unit of time, they've done 1 over, right, that many time units. So if it takes them H for hours, time units to complete a task, then in 1 time unit, the fraction of the task that's been completed is 1 over H. That's the key to these types of things. Now, because of an anticipated heavy rainstorm, the water level in a reservoir must be lowered by 1 foot. Opening spillway A lowers the level by this amount in 4 hours, whereas opening smaller spillway B does the job in 6 hours. How long will it take to lower the water level by 1 foot if both spillways are open? Okay, so you can see that even though we don't have people, this is still a work-related question because each spillway can do a certain amount of work in a certain amount of time. Now, how long will it take to lower the water if both are open? We've just identified our variable. We're asked to find the time think of it as T, time needed, right, to lower the level by 1 foot if both spillways are open. So we're going to let X equal the time in hours it takes to lower it. Again, if it was up to me, I'd make it a T. Okay, so let's translate everything from words to algebra. Time it takes to lower the level 1 foot with A and B together. That's going to be X hours, right? Okay, the distance that A lowers the level in 1 hour. Well, if it takes it 4 hours to lower it by 1 foot, then every hour it goes 1/4 of a foot. And then B takes 6 hours, right? So it does 1/6 of a foot every hour. And then A plus B together, if it takes them X hours, then every hour they do 1 over X. So like if it took them 7 hours, then when they do 1/7, right? If it took them 10 hours, it would take them 1/10 each hour. All right, so we've just identified all that stuff and kind of translated it into math. Now what do we set up? Well, we know that the amount that A does in 1 hour plus the amount that B does in 1 hour has to equal the amount they do together. So that's where we get our fractions set equal to each other. And now it's just a matter of solving for X. Anytime you have fractions and you need to solve things with fractions, just start multiplying to get rid of fractions, right? So multiply through by the denominators. And you don't have to find the least common denominator. Just start picking denominators and multiply, right? Sure, you can see that the least common denominator is 12, but I say it's easier to do it in steps. Multiply both things by x, and then you get x over 4 plus x over 6 equals 1. All right, now I notice that 6 is, so let's multiply everything through by 6. I get 6x over 4 plus x, right, equals 6. All right, I'm still stuck with a 4, or you can sit here and go, hey, this reduces. This reduces to 3 over 2. And so now everything by 2. So x plus 2x equals 12. Sorry, 3x plus 2x. I forgot the 3 was there. Right? Add these together. 5x equals 12. X equals 12 fifths. So if x equals 12 fifths, we just figured out how long it's going to take working together for them to lower it, right? It's going to take them 12 fifths of an hour. Well, what the heck is 12 fifths of an hour? Turn it into an improper fraction, you get 2 2/5. So that's 2 hours, and then you got to do 2/5 of an hour. Well, 2/5 of an hour is really just 2/5, right, times 60 minutes. 60 divided by 5 is 12. 12 times 2 is 24. And that's how they get 2 hours and 24 minutes to lower it by 1 foot. All right, how about problems about distance, rate, and time? Well, anytime you've got a problem with distance, rate, and time, you got to be thinking about distance equals rate times time, the good old, standby formula that you're going to use all the time. Let's put it into service here. A jet flew from New York to Los Angeles, distance of 4,200 kilometers. The speed for the return trip was 100 kilometers faster than the outbound speed. If the total trip took 13 hours of flying time, what was the jet's speed from New York to Los Angeles? All right, so we read it all the way through. We identified what type of question it is. It's definitely a distance equals rate times time question because it's talking about distances, rates, and times. Now we can identify the variable. It wants to know what was its speed from New York to Los Angeles. So S is going to be the speed from New York to Los Angeles. I'm going to draw a picture. So here's LA, right? Here's New York. It flew from New York to Los Angeles and then back to New York. And it wants to know what was the jet speed from New York to Los Angeles. So it's looking for the speed along that trip. Now the speed, so it says a jet flew from New York to Los Angeles. So this is our first trip. And then the speed for the return trip was 100 faster. So doesn't that mean on this one we went S plus 100? If the total trip took 13 hours of flying time, and we know the distance, right? We can figure everything out from this. So distance equals rate times time. Or, since we don't know the rate, maybe we want to solve for that, right? Distance equals rate times time. We don't know speed, right? We don't know time, right? So we could think of rate equals distance over time, or we could think of time equals distance over rate. There's all sorts of ways you can play around with this formula depending on the information you have. Well, here we have distance and we kind of have speed, but we don't know anything about the time. So we'd want to go ahead and solve for time and say time equals distance over rate, and that's where we get this one. And then the same thing down here, right? Distance over rate, and that's where we get that one. All right, now what do we know about those two times? Well, hopefully you're all screaming at the screen. We know that they have to add up to be 13 because it said the total trip took 13 hours. So that time plus that time equals 13. We put in our two formulas. 4200 over S, blah, 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 equals 13. You're going, oh no, more fractions. But remember, the rules never change. When we have fractions, multiply by our denominators. Now, instead of thinking of a common denominator, do it in pieces. Multiply this by S and this by S. And you kill off the first fraction. You get 4200 plus 4200S over S plus 100, right, equals 13S. Now, we still have this bottom, so we're going to multiply everything by that, and we're going to get 4200, right, times S plus 100 plus 4200S, because these will just cancel, right, when you multiply by S plus 100, equals 13S times S plus 100. Now your fractions are gone, and now it should look a little better. All right, so here's where we're at. Now we do a little math. We distribute the 4200 times the S plus 100, and this gives us 4200S plus 4200S gives us 8400 of them, right? Then we do 4200 times 100, and there's 420,000. Then we do this distribution, and we get 13S squared, and then 13S times 100 is your 1300S. All right, now we see that we have a squared piece and a linear term and a constant. We're thinking, well, it's a quadratic. We got to solve it as a quadratic, which means we got to put everything on one side set equal to 0. So we bring both of these two pieces over, combine this one and this one for your 71. This becomes negative, and then there's our quadratic. Now, this equation does in fact factor, but it's kind of hard to figure out what those numbers are, so it's probably a lot easier to just use the quadratic formula in a calculator. And when you do that, you get 600 or negative 53.8. Now, since S represents speed, we throw out the negative number because, yes, I know in physics a negative speed just means speed in a different direction, but that's not really speed, that's velocity, right? And we weren't talking about velocity, we were talking about speed. And when we talk about speed, going left and right or up and down, your speed is still positive. So you can't have a negative speed. So we throw that out, and our answer is 600. And we are done.